Thank you for the invitation. This is a great school. The two talks I heard today are really tough act to follow. Now, Michał just said that I'm going to talk about fundamental physics, and that's true. But the emphasis is on the first syllable. You know, fundamental, first syllable. Okay. I actually have an artistic kind of title, Light on Dark, and you will see where this comes from. So I plan to, as I was asked by Michał, to give an introduction to ultralight dark matter and why are we talking about ultralight. And see, dark matter is strategically written so you can hardly see it, you know. But you can feel the gravity of it. And then I will tell you about how dark matter of this particular kind of dark matter is very much like chaotic light. And Michał is, I hooked him successfully already, so stay awake. I'll then tell you about some of the recent experiments we are doing to look for different kinds of this ultralight dark matter, and then I'm going to, in the end, switch gears completely and spend a few minutes telling you about something that I'm personally very excited about, and it's a new tool that is at the boundary of between dream and reality. It's right in between currently, and this could be actually a very new and important tool, in my opinion, for fundamental physics and for discovery in the future. So I want to let you know about this. So I really liked the cosmology summary this morning because it emphasized the fact that actually there are huge problems, and we can, you know, think of them as elephants in the room. This cartoon shows one elephant in the room, and what I meant by this elephant is that actually we do not know what most of the matter is in the universe, and this is like an obvious problem. We can be very proud. You know, in Germany we say professor, doctor, or actually university professor, doctor, and we are all going there, you know, wearing these titles, but we don't really know what most of the stuff in the universe is. So I think we should like anyway. So we're trying to address this, and so I don't need to, so I don't need to again tell you about all the pieces of evidence that there is something wrong there, and something that might be explained with the dark matter. But I thought I'm going to list, just to remind you, some of the candidates for what dark matter could be, or what could potentially mimic it, as we heard. So the first item here that I'd like to put is actually something that I find most intellectually attractive. It's that there is no dark matter, but we just don't understand how gravity works. After all, we know about dark matter through various gravity effects. So the problem with this, as we heard, is that there are all kinds of spatial scales on which we get the evidence. I got caught. Let me put this in the pocket so this doesn't happen again. The smallest scale is galactic scale. Okay, so this for the rotation curves of the galaxy. The next one is galactic clusters, and so on and so on and so on, and so on, until we reach the size of the universe, the cosmic microwave background, and the whole universe. The fact that we would need to make a modification to gravity on all of these spatial scales simultaneously makes it fundamentally difficult. For instance, in physics, we often just assume some additional interactions or something, and we can just say, okay, so gravity is not really the, you know, 1 over r potential that goes to infinity. Maybe we need to cut it off, which people call sometimes Yukawa cutoff, some exponential cutoff on a bigger scale. But that's a problem, because we need all of this different scale, and so such a simple modification doesn't work. And so people go into some degree of sophistication, and this modified Newtonian dynamics about which we heard this morning is one of the attempts. Now, I put these frowny or smiley faces here to show you how the community as a whole, so if you were to do science by democratic vote, which you shouldn't do, but I think science is very individualistic, and sometimes, you know, this lone opinion can prevail. Nevertheless, so this kind of gives an assessment of what the majority of physicists working in the field would see, and this is not really doing super well, except for the proponents of some of these things. Nevertheless, I think one really should keep an open mind for what can be going on here, and consider different possibilities. And I need to confess to you that I actually got involved recently into one such attempt. The story of this is that, you know, many years ago, when I was an undergraduate student in Novosibirsk, at that time Soviet Union, one of my professors who taught me physics was Professor Dmitry Ryutov, he then later on moved to the United States and actually retired a couple of years ago, and so I invited him to come and spend some time at our institute in Germany, and we worked on a problem of our mutual interest. So in principle, we kind of work in more or less non-overlapping areas. He's an expert on plasma physics, and I'm not. But anyway, the idea that we were trying to look at is the following. We think that a photon is a massless particle. But physics is an experimental science, so we should go and see what the limits are. And if you open, you know, the place where you go for information about particles, the particle data booklet, and you open photon, you find, first of all, that the limit comes from the work of Professor Ryutov, actually, and that the limit is currently 10 to minus 18 electron volt. So it could be, experiment says, could be up to 10 to minus 18 electron volt. Now, if a photon is actually a massive particle, we need to rewrite our theory of electrodynamics a little bit. It's been done. If you like Dave Jackson's book on classical electrodynamics, it's a wonderful book. You know, you go to chapter towards the end. I don't remember the number, and there is a chapter. It's called Proca electrodynamics. Proca is the guy who worked out these Maxwell-Proca equations. And the question that we tried to address was the following. If indeed a photon has some mass, let's say some small fraction of the current limit, let's say 10 to minus 23 electron volt, 10 to minus 5 of the current limit, then what effect this new electrodynamics would have on the plasma in the galaxy? You know, most of the material is actually ionized, and so it's actually a plasma, and you have to see what happens. And as we started working on this, we started getting an interesting result, that it is actually not a problem at all to get these additional forces that would reproduce the flat rotation curves in the galaxy. And so we got really, really excited about this. Unfortunately, pretty soon we had to cool ourselves down a little bit, because you know, a theory makes predictions, and so one of the predictions that our picture made is that old stars like our sun should move on orbits with very high peculiar velocities, like highly elliptical orbits, and that doesn't seem to be observed. So it looks like there's a little bit of a contradiction with this. And so now it's the status of this is not as attractive as we were hoping, but nevertheless we think that the point is that one should keep the mind open to various possibilities until we discover what dark matter actually is. So all kinds of things have been considered over the years, that it's some kind of black holes, some planetary type objects, maybe interstellar gas that's less luminous than we would think, and this stuff is more or less ruled out, even though still once in a while there are some papers appearing that says that maybe something could be, but this is sort of a general situation. Now I tell you something. If you want to decide the probability of which candidate for dark matter is the most probable, and you want to decide it based on the amount of money spent for the search, then for sure, it's a weakly interactive massive particle, because it's really a big industry. Particle kind of physics style detectors with tons of materials, with years of work. And actually there is a very good reason, because the particles that would have sort of normal particle masses, say some GeVs, maybe 100 GeVs, so typical masses for particles, but interacting only at the strengths of the weak interaction, fit extremely nicely into particle theories and would make a nice picture. The only problem with these guys is that people are looking and looking and looking and can't find them. And so as they can't find them, then people think, okay, what else can this be? And so then this whole new class of things is coming up, and it comes under this rubric of ultralight bosonic particles. And I will explain why they're bosonic. Yes?
My question is, because I was wondering that it's not that the fact that they interact by gravity does not imply the scalar or pseudo-scalar symmetry?
No. So basically, all of these, in order to be a candidate for dark matter, it has to have gravitational interaction. So now assuming that we understand how gravity works, and that there is actually some particle which we don't see because it doesn't interact or very weakly interacts with the normal matter. And that
gravitational interaction has a scalar symmetry by itself.
No, it could be anything, but it has to be, it will have to be bosonic, and I will explain now why. You probably know. All right, but I want to say that this zoo of these particles has a great variety. So the most popular thing is axion, which is actually a particle, still hypothetical particle, because nobody has seen it, that was introduced in the 70s for a completely different reason. There is this problem in high energy physics that's called the strong CP problem, which is that the quantum chromodynamics, the theory of strong interactions, allows you to have CP violation. That's not a problem. There's a nice place to write it in. And but experimentally, again, we search and search and search, and we can't find it. And so it means that some parameter called the CP phase or theta term, which could be, if you don't know anything, anywhere from 0 to 2 pi, happens to be less than 10 to minus 10. And people don't like this kind of coincidence, you know. And in order to make this not a coincidence, but sort of a consequence of the properties of things, people have introduced these pseudoscalar particles, spin 0 intrinsic parity minus particles called axions. And later on, it was realized, oh, wait a minute, this is also a good candidate for dark matter. And this would be very nice, because then we can kill one or two birds with one stone, as they say. So that makes it very attractive. It's nice to solve all your problems in one go, right? there is a generalization of axion called axion-like particles, or ALP, and this is just as good as axion, except it does not solve the strong CP problem. Okay, so it's a less attractive candidate, but on the other hand, the parameter space for it is wider, and in principle, it's okay as well. So we look for ALPs and axions. When we don't have sensitivity to look for axions, we will look for ALPs. So these are pseudoscalar candidates now. Somewhere in the depth of string theory, there is a prediction that there should be a scalar particle called dilaton. It's spin 0 also, but intrinsic parity positive. And it turns out that this intrinsic parity is very important, because when you write your theory, you would see that these guys interact with spins of particle, and these guys do not interact with spin of particles, but effectively affect the values of fundamental constants. And so for these guys, we usually look with something like nuclear magnetic resonance or magnetometers, and these particles are good for clocks, the subject of this school. So these are very important. All right, but our imagination doesn't have to stop on scalars. There could be also vector candidates, and you might have heard about dark photons, and they come in this category here. Michał is very skeptical about something, but I don't know about what. Tell us.
No, I'm just skeptical about that photos and the vector tensor.
Okay, well,
Maybe I'm not so open-minded.
yeah, theories actually don't really like tensors very much, but for the reason that they're hard to deal with, but no other reason, I don't know. I like tensors myself for some reason. But anyway, so this is the situation. Now, I am sort of a newcomer to this field. I've been working on this maybe since 2013 or so, and so I didn't know very much, and then I had to learn this stuff. And as I was learning this, I discovered something really, really interesting, which is that even though people do not know what dark matter is, but if you it's like a detective that arrives at the scene of the crime. He don't know who the criminal is, but there's little clues here and there, and eventually a file is assembled, and the detective knows a whole lot about it. I'll show you that this is what is happening with dark matter. So the first thing, sort of as a preliminary, is that from these rotation curves we can calculate roughly the density of dark matter in the galaxy, and it comes down to something like 0.4 GeV per centimeter cube. If you are not comfortable with these GeVs, you should be, but if you are not, this is this number corresponds to about 1 proton mass equivalent of dark matter per 3 cubic centimeters, something like this, or 1/3 of a proton per cubic centimeter. Now this table is maybe 10 to the 23 protons or something per cubic centimeter, so that is a very small density, 1 versus 10 to minus 23. But the galaxy is big, and this happens to be the dominant matter in the galaxy anyways. Okay, so now this is easy. Now the second thing is very interesting, because I'm going to prove to you that dark matter is non-relativistic, and the fastest it can be moving is 10 to minus 3 of the speed of light. It can move faster. And say, how can you really say that, because you don't know what it is? Well, I can show you. If I take this laser pointer, and I'm going to sacrifice this laser pointer for science, and I throw it, it comes back. Then I can throw it higher, and it comes back. But if I throw it at, what is it, 11 kilometers per second, this is the escape velocity, it's gone. So if I have dark matter, that's supposed to be in the galaxy, and it's moving very fast, it's going to exceed the escape velocity in the galaxy, it's going to go away from the galaxy. And that escape velocity happens to be 10 to minus 3.
Only under condition that is not produced all the time.
Right. If you're yeah, but if it's produced all the time, I mean, that's the thing. There are problems with this, right? Somehow, because you cannot produce mass, right?
Well, you can get rid of the mass in the black hole, so I can produce in the open light system.
Okay. This is this homework. That's homework. That's homework. Good. Right. So that's the first nice thing about it. The second thing is this is now really interesting. I'm going to make conclusions about the spin of the particle of the underlying dark matter, and I'm going to try to convince you that if the mass of the particle is less than 20 electron volt or so, it has to be a boson. It cannot be a fermion. And you might say you should have resistance, because you don't know what it is, and now you tell me about its spin, boson or fermion. What is going on? And it's very, very simple, ladies and gentlemen. Let's say I assume, for simplicity, that dark matter is made of some particle with mass m. I know the density of the density, okay? So in order to find the number density of particles, I just divide this number by the mass, and then I have the number density. And then I'll show you actually the calculation in a minute, but we've all done this. You know, we can calculate the density of states, and two fermions cannot occupy the same quantum state, and so there is the Fermi distribution, and it better be that the Fermi velocity is less than the escape velocity. Why? Because if it's larger, my dark matter will go away from the galaxy, and it's confined to the galaxy. And the numbers come that it's lighter than 10 or 20 electron volt, then it has to be a boson. Amazing. So here's, by the way, I always tell my students who prepare to give talks, don't like copy pages from a book in your talk. It's very bad style. But here I did it, first of all, because it's from my book that I copied. And second of all, just to show you that the entire calculation with all the details is just less than 1 page. I'll tell you another thing. Maybe it doesn't click at the moment, but it's this exactly same calculation you do to calculate what's happening with electrons in the metal. Exactly the same calculation. So density of quantum states. There's 2 for polarization. This is, you know, d3p, d3p, d3v over 2 pi h bar cube, blah, 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 blah. You put in, you know, well, that's it. That's the whole calculation. And then you get the mc squared is equal to 20 electron volt. That's all. By the way, the book is called Physics on Your Feet. And it's not in the first edition, but it's going to be in the second edition that is currently in preparation, and it's co-authored by Professor Alexander Sushkov of Boston University, my colleague, dark matter hunter, and also my former PhD student. And this book is to help PhD students prepare for oral exams, and so in order to relieve the stress, it is full of silly jokes and cartoons of this sort. So anyway, we can continue this file about dark matter. So when we have a whole bunch of bosonic particles with high density, sometimes it's more convenient to think about them as a field, as a classical field, so to say. rather than individual particles. And then another amazing thing that we can say is that this picture leads us to say that these particles are a bosonic oscillator with a quality factor of about 1,000,000. And again, you should have resistance. You keep telling us detailed information about dark matter, and we don't know what it is, not a clue what it is. How can this be? Well, actually, it's all the same thing. This number, 10 to the 6, is this number, 10 to minus 3, 1 in the power minus 2. So what's going on is, let me say, the scientific words is that scalar fields are governed by this Klein-Gordon equation, if you remember your particle physics. And Klein-Gordon equation says that this field should be oscillating, and the oscillation frequency is the Compton frequency, which is basically the mass in the frequency units. Mass, or I should say energy, total energy in frequency units. But let's remember, this is a non-relativistic particle, okay? And let's remember what an energy of the non-relativistic particle is. And you better remember this on your exam if you're a PhD student. So the energy is mc squared, that's the leading term, right? Plus what? Thank you very much. Well, and there's actually there's a famous story. I don't know if you know that the people are having a picnic in the park, and all of a sudden, you know, some guy comes riding very fast on a bicycle and crashes into the tree, and they run up to him, and he's all, you know, covered in blood, and then they fear that he has died, and they assemble around him, and he opens one eye and says, "It's very good, it's over 2." They say, "Well, the guy must be crazy. What's over 2? mv squared over 2." Yeah, anyway, so it is mv squared over 2, and so different particles move with different velocities, and so their frequencies are different by about 10 to minus 6, and that gives you this coherent sort of, Q factor for this oscillator.
I was just curious, what is that dg? 10 GeV per cubic centimeter dg?
This is dwarf galaxy. So if you can, forget it. It's a detail.
It's more dense.
Yeah, different types of galaxies. I should remove it. It's just at this level, it's a distraction. I'm sorry. Yes, so that's actually now again from the same book already actually, yeah. So this again the density 0.4 GeV, and this shows you what is, if you assume for instance that the frequency of the particles, the Compton frequency is 1 megahertz, then it's 10 to the 17 per cubic centimeter. And then this is a little calculation of the coherence time. So again, putting these numbers, for example, if it's a megahertz oscillator, the coherence time is 1 second, and the speed is 10 to minus 3 c. So this is the difference between Compton and de Broglie wavelengths. So de Broglie wavelengths is you have to multiply the coherence time by this 10 to minus 3 c, and then you get the sort of 300 kilometers, the coherence length for this particular values of parameters. It turns out that this leads to an interesting picture of what dark matter is. And a lot of people have difficulties with it, actually. But I'm convinced that unless these particles both condense, and we can discuss a little bit later whether they are both condensate or not. If they are not both condensated, then I think they look pretty much like a laser speckle. I don't know if the lights allow you to see it, but this is a laser speckle, and moreover, it's like the speckle has these dark parts and bright parts, and and it's sort of breathing with a coherence time. And this is a very important fact that was, I believe, overlooked by people in the serious literature, and I'm going to show it.
I was always convinced that the dark matter is standing, but only in statistical way. So I mean, every single particle is moving in different direction.
Yeah, that's right. And then, so the field, you can write then the field for every axion, let's say, and then you have a whole bunch of them moving in different ways, and you add them like you would add fields from, say, different laser beams or something, and then you would see that it's all like breathing around. This way, it turns out to be very important. Let me just continue a little bit because I find this very exciting. I hope you do too. There is another conclusion we can make that we can say that it's a light bosonic particle, but we should have shame. We should stop at some point, and we should have shame at about 10 to minus 22 electron volt. You know why? Any guesses? It was already discussed, because the de Broglie wavelengths at this point becomes equal to the size of the galaxy, and the dark matter has to be confined to a galaxy. Can't work if it's lighter than 10 to minus 22 electron volt. Now there are some people, some serious people, who think that dark matter could be a BEC, and then actually some of the things I'm saying would modify, because then basically you would have all of this field in the ground state, and then the coherence times could be longer. There's an ongoing debate about whether dark matter can be a BEC or not, and I think I think actually it's a little bit of a subtle question, and then in order for a system to come to BEC, you need some kind of interactions to make this happen, and if you don't have any interactions, the transition to BEC can take a very long time, and so maybe it's not a BEC. And then there are other people who point out to some experimental observations, like the sort of the structure of dark matter, that may point to the fact that this is BEC. But the good news is that if it is BEC, it's going to be even easier for us to find. So we can just assume that it's not at first. All right. Now let me tell you. First, before I tell you about this, are there any questions?
So the common assumption is that the dark matter particles only interact among themselves with gravitation. There is no.
Yeah. So we have evidence that that dark matter particles not only interact weakly with normal matter, but also with dark matter, and that comes, for instance, from the bullet cluster and so on. So
yeah, because I have just to check, because I was quite sure, and I just confirmed that I saw plenty of graphs that ended at minus 25.
yeah, yes. So first of all, when you're doing experimental limits, you can be agnostic. Okay, so this is some kind of a theory. Believe it or not, what I doesn't look like theory, but it is. And then if you assume that this field is not all the dark matter, then a lot of these restrictions, for instance, if some component of dark matter is bigger than the galaxy, it's fine. It just can't explain the. It's yeah. So suppose we want to look for dark matter, but here you should stop me and say, what do you mean look for dark matter? We started this discussion because we found that there is dark matter already. What do you mean? Yeah, just look at the rotation curves. Dark matter is there. Well, what I mean is that we are looking for some kind of a non-gravitational signature of dark matter, and that's what we mean by searching for dark matter, non-gravitational direction. So if we just confine ourselves for a minute to axions and Alps, these are the particles beyond the standard model, but they are not crazy particles. There are some rules about how you write Lagrangians in the quantum field theory, and you write that for pseudoscalar particles, and you find that it's actually not so many different ways how these things can interact with matter. So, so now, just to explain the notation, this A would be the amplitude of this classical field. I'm no longer talking about individual axion. I'm talking about the sort of this classical field corresponding to a bunch of them. This F mu is electromagnetism, and so this term is responsible for interaction of axion with photons. In particular, there are many experiments where people are trying to, say, pass a laser beam through strong magnetic field, and due to this interaction, you can produce an axion, and then you can also detect the axion that comes into a strong magnetic field and in a cavity and produce a photon, and then you detect it, and so on and so forth. So most experiments are based on this term. There is a term that's analogous to this, but instead of the photons here described by the F mu tensor, you have the gluons, okay, inside of protons and neutrons. And this term has a very interesting effect. It's a CP violating effect. So such interaction produces an electric dipole moment of the neutron and the proton and the nucleus, for example. And do you know that a little bit about it, or should I explain why a dipole moment violates P and T? It'll lead me astray a little bit, but
I think you have plenty of time.
I don't think so. Okay. Yes. So first of all, if I have some particle, I have a spin, or okay, call it total angular momentum spin, whatever. Let's call it S, like intrinsic spin, for example. And if I have any kind of a vector quantity, this vector quantity should be parallel. So, for instance, if I have a magnetic moment, it's along this the spin, and it could be, for example, I don't know. Let me draw it. So this will be the magnetic moment. Okay, it should be collinear, and this has to do, the scientific terminology is Wigner-Eckert theorem that says that all the vector quantities are proportional to the total angular momentum, but the physical content of this is actually so if there were some other directions other than the spin, then you would have a lot of different additional quantum numbers, and if you had additional quantum numbers, quantum statistics would look very differently, and this doesn't happen. So all the vector quantities should be collinear with the spin. Now, if I have for example, some particle whose magnetic moment is opposite to the spin, for instance, right? And then, may I ask, who hasn't seen this before that I'm about to draw? Is there somebody who hasn't seen this before? Okay, 2 people. Okay, good. You haven't seen it? Okay, I don't believe you. You have seen it. Okay. So if you have now the operation of spatial inversion, so mirror transformation, you know that there are normal vectors that flip sign, and there are axial vectors of the type, for instance, angular momentum is r cross p. These are normal vectors, and if you have 2 of them, this flips sign under mirror transformation, this flips sign, and so the product doesn't. And so spin and magnetic moment are such things. As you do the P transformation, you get the same picture. Nothing happens. They both Okay. Now I can also do time reversal. Different color, doesn't matter. Time reversal. And you know, spin is spin, and if I reverse the time, it spins the other way. So my spin will flip now, and the magnetic moment will also flip because it's a magnetic field, and the current is flowing the other way. The magnetic field flips. So I have this picture, and everything is beautiful. I see that if I do P and T transformation, then my magnetic moment remains opposite to the spin, and everything is good. So magnetic moment, thanks God, is allowed by parity and time reversal invariance. Otherwise, you know, a lot of physics we are discussing here would be impossible. But now, say I want to pull the same trick with electric dipole moment. So I'm going to draw this picture. So here's again my spin. And now I'm going to do the same thing, and I'm going to say that I have a permanent electric dipole moment associated with this particle. Now let us do P. And now we start running into trouble, because as we already have seen, S doesn't change, but D, remember, dipole moment is E times R. And R is a normal vector. And my dipole moment now has flipped. So that's bad, because I have in the lab I have dipole moment opposite to the spin. Then I do mirror transformation, and the dipole moment is along the spin. And so somehow now we have a way to distinguish whether we are in the real world or in the mirror world, and this violates parity. Parity is less violated, okay? But if the dipole moment violates parity, I should say. Okay, now we do the same with time reversal, and here I have my spin flipping, and the dipole moment that has nothing about time in it, so it's like this. So we see that magnetic moment is allowed by P and T, and the electric dipole is forbidden. So this term here, coming back to our game here, creates this dipole moment in the nucleus, but it's not a permanent. It's not a static dipole moment, because it's proportional to this axion field. An axion field is an oscillator. Remember, it goes with the Compton frequency of the axion. So this leads to an oscillating electric dipole moment. It's a beautiful effect, and we are looking for it in an experiment called cosmic axion spin precession experiment, electric, and this is in Boston. The third and final way the axions can interact with things is through something that's called a derivative interaction. So here now, instead of the axion field itself, we have a derivative of it. And then we have this current, fermionic current. So this looks horrible, but if you take the if you write it in the non-relativistic notation, here you have, let's say, a gradient of a pseudoscalar quantity times spin. So this is very much like B dot S, like the Zeeman term. And this is another way. So if there are gradients in our field, we can feel the sort of the axion wind. And so the Casper wind experiment of Mainz is looking for it. A network of sensors called NOM is looking for it, and a beautiful Italian experiment called QUAX, which has nothing to do with ducks, but I think it says from Latin quore axione or something like this. looking for axions. All right.
Just a small question, I'm not sure whether it's thing, but one might likely think that the first term, coupled to the electromagnetic field, would also contribute to generating an electric dipole moment. Is that true, or is it not possible for some technical reason? Maybe we can discuss that.
I haven't heard. Maybe in some. I haven't heard about it.
An idea of why it's perhaps not possible, but we can discuss that.
Yes. I'm sorry. I'm actually a plumber. This is what my theory friends are telling me. Yeah. So I have to think of a good reason. I haven't heard of this term generating the.
I think I have an idea why maybe it's not possible, but we can discuss.
Yeah. Okay. Good. Anyway, just briefly, the Casper program sort of is building up these experiments. It takes a little bit of time. All of these experiments are based on nuclear magnetic resonance, but I'm very happy to report to you that actually in the last year we have published first results of this program, and these results came from sort of an somewhat unexpected direction, because in another part of my laboratory we're doing this very strange thing that's called zero field nuclear magnetic resonance, and this is sort of a way of doing magnetic resonance work, by the way, initially unrelated to dark matter research completely, and it's a strange way of doing nuclear magnetic resonance where instead of large magnets as strong as possible as normally people use in NMR, we actually use a multi-layer magnetic shielding, because even the Earth field is way too much for us, and then we do this kind of work. I don't have time to tell you, but maybe if you have questions, I have some backup slides to tell you how this works. But it's also an NMR experiment, and in this experiment we were actually able to start cutting into interesting ALP parameter space, and I must show you this and use this as an example of the, how people present data in this dark matter search business. So typically you have the mass of the dark matter particle here. So mass is the same as the Compton frequency. So here we have Compton frequencies, and here is the coupling constant that characterizes the strength of the interaction. So if you have not seen the effect, it may be that the particle is not there, but it also may be that this interaction constant is small. So this range of masses corresponds to frequencies from about 10 hertz or so down to 1 inverse year. Very slow oscillation frequencies. And so we're working on it. So there are two versions of the experiment, and so we hope to do much better soon. And but these are first results that are in these two papers. This is in Press in Science Advances. Now, as we were working on this, we realized that a lot of authors in the field have treated the low frequency region here not quite correctly, and this has to do with the stochastic nature of dark matter that I already mentioned. And if you are actually interested in some details here, there is a preprint on the archive over here. And the idea here is that if you are located in some particular space, place in space, right, on Earth, and you're surrounded by this breathing dark matter, and then you do an experiment, and you have not seen the dark matter. And so there are two possibilities. One possibility is that it's not there, okay, you're looking in the wrong place, and another possibility is that you have been somewhat unlucky and you turned your experiment on in the time where the field was passing through zero, and you have to account for this possibility when you draw your exclusion plots. And this hasn't been done. And let me spend a few minutes explaining why I keep insisting that dark matter is just like chaotic light. And here I have a question for you. So suppose I have some kind of a thermal light source like this. And just to make the discussion simpler, I'm going to put a polarizer, so only one polarization direction will be transmitted. And then I detect it on the detector. And just to simplify the discussion, I'm going to assume that the entire light bulb here is in one Fresnel zone, so I don't need to worry about the difference in the propagation and so on. So then I'm going to ask you a little question. This is a test. So what is the most probable instantaneous intensity that I would detect on this detector? So this is an intensity detector, and its response time is short. So let's say this source is characterized by some coherence time, and my response is shorter than the coherence time. What is the most probable intensity? Somebody knows. What is the most probable intensity that I will detect? Thank you very much. Who said that? Good. It's 0. And it doesn't matter if this would be a megawatt light source that will burn everything in its place. Still, the most probable intensity is 0. And how is this possible? Well, actually, I recommend, well, there are two books I can recommend. One is my favorite, Rodney Loudon's Quantum Theory of Light, from which I learned, and another one is, of course, our book. Yeah. And the way you can think about it is that this chaotic light source consists of a whole bunch of individual oscillators, and they radiate randomly. And so you can have this phasor diagram if you want. This is one phase of the field is another, and these are a bunch of randomly directed vectors. And then the total field is bosons, right? So the bosonic field, you add contributions for each individual emitter, and so you have kind of a diffusion in 2D. And then if you work it out, it's really a distribution like this, and the most probable intensity is in fact 0. So there's a simple calculation you can do. For the laser, by the way, it would be different. For a laser, you would have some distribution like this. That's the difference between laser and chaotic source. And the whole calculation, again, is right here. It's basically 2D diffusion, or also known as a drunken sailor problem. Right? Anyway, so we've done this for dark matter, and it's basically the same. And this has to be taken into account. And we looked at various papers that were published, and we find that typically we call this stochastic correction, or if you want. And so this is some kind of a typical exclusion plot. Goes, by the way, to 10 to minus 24, as you as you said. But it's a typical correction, and it's about an order of magnitude to take that into account. So if you go to that kind of ranges, you have to take care of this as well.
Minus 15 is something like second, yeah?
Huh?
Minus 15 is 1 second.
Yeah, 22 is 1 year, and then a year is 10 to the... okay, that's a nice number. 1 electron volt is 2 times 10 to the 14 hertz. So good. Also, for the wind experiments, you need to worry about the direction of the velocity. It's another correction. But let me. The time is ticking. I have to stop at.
No, you can. I mean, you should stop, but
Yeah, I'll stop. Don't worry. When?
Somebody will tell you off your projector. I mean, the casual time is still 3p.
Yeah. Okay. Good. But now we're coming to the part that's more relevant to clock. So that's a little okay. So Stochastic part is relevant for any bosonic dark matter. Before that, I mentioned briefly the axion. So now I want to talk about dilatons. And for me, the story starts with Mina Arvinataki. She's a professor at the Perimeter Institute. And she was pointing out at some point that these dilatons should effectively act as, they should change the fundamental constants, and so should change the clocks, and that these effects can be looked at using clock comparisons. And her students and her wrote a nice paper. And my postdoc, Nathan Leifer, read this paper and came to me very excitedly, saying that, hey, we can do something about it. In our lab, indeed, we have a device that is a very bad atomic clock. It's an atomic clock, but very bad one. But it is a differential atomic clock, and it has some unique properties. And the idea here is this is a dysprosium atom, and we actually had this for many years, looking for variation of the fine structure constant alpha. And you know, when you build a device, you have to, with the property management, you have to obtain stickers to put on your apparatus. So we call this device alpha variometer, you know, the device that is measuring variation of alpha. So we had that, and the idea is that this dysprosium atom, which has a very, very complicated spectrum, there are hundreds and hundreds of levels here, but there are two levels of opposite parity here that happen to be almost degenerate, or they have almost the same energy. Now, if alpha is changing, then it is an important part. So the energy of an atomic level, it consists sort of gross energy, fine structure, and hyperfine structure. And these contributions, they have in principle different weight in different configurations. And fine structure scales like Z alpha squared, where Z is the charge of the atom, or an atomic number. And so if you have levels that have different fine structure contribution and alpha is changing, then these levels will move differentially. And that's what we actually exploited here, these two nearly degenerate levels. And we actually didn't even have to do a new experiment to look for this effect predicted by Asimina. We just were careful to record our experimental data from before on disk and timestamp it, which I actually highly recommend to everybody who is doing any kind of precision work. Store it, timestamp it. Nowadays you can do GPS timestamping, you can do good clock timestamping, even better. The storage is cheap. It's your PRLs of the future will be sitting there waiting for you. Anyway, so that's what we did. We actually analyzed a couple of data sets. One was several days long and one was several months. So we were able to obtain these limits on this dilaton interaction. And in our paper, which was a PRL indeed, we wrote that when serious clock people start looking into this, not us, then they can do much better, and that was what we published there in that paper. And indeed, we were super happy to see that already 1 year after that, I think the third group was one of the first groups to publish very nice results, and now a lot of people are doing this. I don't know if you are playing this.
Yeah, we also publish.
Yeah. And Junier and everybody is doing this game. So Good. Yeah. So I hope I have time. I'll tell you another thing that I think we did very poorly, but for the first time, and then maybe everybody will be doing it again. But it's not so. That's not actually not so bad. I must say. So it's 10 to minus 15 kind of variations or better.
Actually, that's why, because at minus 15, the time coherence time is around below 1 second. So
yeah, that's not a problem. Yes.
Because for looking for that, you actually making a parallelogram. So you fit the sinus.
Yeah, that's.
So how you include something that is below the coherence time, and your data are longer than coherence time. Because if you have data from here, but if the effect coherence time is shorter than 1 second, then it loses phase every second. That was one thing that in our data we have to cut it because we were not able to correctly quantify something that is faster.
Let's discuss. Let's discuss. Yeah. Okay. Yeah. Good. So what I want to tell you now is something very new and very exciting, and this has to do with the work of Gilad Perez of the Weizmann Institute and his team, and they are looking at a candidate that is called a relaxion, and this is a word play. You see axion here, and this is an axion that undergoes relaxation oscillations in the early universe. And this is an attractive candidate to explain yet another problem in particle physics called the hierarchy problem, which is why the masses of particles are so much smaller than the natural scales of physics, like the Planck mass or the grand unification mass, which are something like 10 to the 16, 10 to the 19 electron volt, and we are talking about particles of maybe GeV or something, so many orders of magnitude. So anyway, it's an attractive particle, and to me, the most exciting thing is that this particle is simultaneously a scalar and a pseudoscalar particle. So it has like intrinsic violation of parity, and so it can be looked for in principle by clocks and by magnetometers and NMR at the same time. There's also some possibility that there could be a local enhancement of this bosonic density near the gravitational objects like Earth or the Sun by many orders of magnitude. And this would make all of our experiments much more sensitive, by the way. So you might want to look this up. The one thing that we took from discussions with Gilad is that he kind of prefers the mass range that is a little bit faster, and this is way too fast for precision clocks. But we started thinking about what really is happening here, and we realized that what Gilad is saying is that you take an atomic energy level, and this level goes like this at some high frequency. Can we measure this? And we decided to have a little demonstration of this. We thought it was going to take a weekend, so we called it a weekend experiment. It took really a couple of months in the end, as usual, but it's a really very simple experiment. And this was done by Dionysis Antipas, Oleg Tretiak, and Antoine Garçon in my group. And we consulted a lot with Rui Ozeri, a brilliant experimentalist at the Weizmann Institute. And the idea here, this looks like a complicated diagram, but it's something incredibly simple. It's basically saturation spectroscopy. So something that everybody who logs the lasers is doing essentially every day in the lab, we decided to use like a fancy version of it called polarization spectroscopy that gives you a dispersively shaped error signal. And so we take a laser and we stabilize it to a cavity. This cavity, when the constants change, the cavity cannot actually respond very fast. And so this is like our flywheel, but atomic energy levels are going fast. And what we do is we just take our error signal and send it into a spectrum analyzer. That's the entire experiment. And when we did this, we did it on a couple of transitions. So at first we thought that maybe we go to a narrow transition, and this is 6s to 8p3 halves in cesium. And that's what we saw. But then we realized that actually, if we want to go to higher frequencies, then if we go beyond the lifetime, inverse lifetime of the transition, then the transition itself starts to integrate the signal. We're acting like a filter, and so it cuts us off here. And then we actually decided to go back to 852. It's just the D2 line of cesium. And so we were able to get variations of like something like a few times 10 to minus 15 with really a very, very simple apparatus. We also got excited, of course, because we saw some signals. Those turned out to be not dark matter, unfortunately. But right now, we are actually building a new version. This level is limited by something extremely silly. It's basically limited by the fact that we have a cheap spectrum analyzer that scans the frequency instead of taking all the frequencies simultaneously. So now Oleg Tretyak has built a homemade device that's supposed to take all the data simultaneously, and we are shooting at 10 to minus 18. But again, when serious people will start doing this, I think that you can do even much, much better if you're really serious at this. So this is on the archive if you are interested, and it should appear, actually it's been accepted to PRL. The official name of the experiment is WRESTLE. We are kind of proud of it. And that stands for Weekend Relaxion Search Laboratory. Yeah. Right. There are a few. Let me now accelerate here. 5 minutes, yeah?
No, 20.
Ah.
20 minutes.
I thought I need to stop and have questions, but okay, you can ask questions. So I'm not going to stop you, but you ask questions.
I was talking over the house, and that doesn't care very much.
And you think I should do like you, yeah? Okay. Anyway, so we are all interested in networks, and so I think this was the, I don't know, but I think this was the first dark matter search network, and the story of this. Let me tell you the story of it. It was in my office at Berkeley, and two of my former students were sitting next to me, Shimon Pustelny and Derek Kimball, and I think Wojtek Gawlik. We either I can't remember if he was there visiting also or we Skyped him. But anyway, this was the how many, 4 guys discussing this at that time, and the sentiment was the following: look, we are all building magnetometers and trying to make them as sensitive as possible. Now, after we build a magnetometer, what do we do with it? And what we do with it is we stick it in the best magnetic shield we can make, 4-layer, 5-layer, very fancy with, and then we look at this super sensitive device that's measuring nothing. Now, if you ever looked at an experimental trace of like noise, right? So you look for it for a few minutes, and then there is, psychologists call it constructive boredom, right? So you look at the noise, and you start seeing things just in a few minutes. You say, oh, I saw something. And so the crazy idea that we had during that conversation is that suppose we have one of these devices at Berkeley and another one in Krakow, where Szymek Pustelny makes them, okay? What if we were to correlate these things? We can time them together with GPS or something. What do we correlate? Can we do something useful? Sometimes you see noise peaks where maybe your colleague dropped a screwdriver, and even though it's in the shield, you still see falling screwdrivers through the shield. But it's very unlikely that two colleagues will drop a screwdriver in Krakow and in Berkeley at the same time. So we were wondering, can you do something with this? We didn't know what. But we had a hunch that maybe it could be useful. And we said, okay, good. It's a nice idea. We got excited about it, and then we started calling our theoretician friends, one after another. And the reaction was very interesting. Every theoretician said, wow, what a great idea. Let me get back to you tomorrow. I'm sure something good can come out of this, some interesting physics. But then they wouldn't. And this continued for about 2 years. So we had this conceptual idea. Everybody would say it's wonderful, but nobody could actually tell us what it is good for. And finally, I called Maxim Paspelov, also at the Perimeter and also at the University of British Columbia, now at Minnesota. And Maxim actually did come up with something, which is a model for dark matter, where dark matter is actually something that's now called topological dark matter, that there are regions of space with different values of these scalar fields, and then the energy is like in a condensed matter is in the boundary. The boundary is very energetically expansive, and these domain walls is what dark matter is. This is very controversial because a lot of people think that such topological structures cannot survive from the early universe. But there's a nice ongoing debate. So lo and behold, we built our magnetometer network, and it has about a dozen sites everywhere. And to my surprise, now it's 2017. It was already about 50 scientists all over the world working on this. Then Maxim Paspelov and Andrei Derivenko, they took this idea one step further. They said, let's look not at the pseudoscalars, but at the scalars, and then scalars do not interact with spins, they change fundamental constants, so we need a network of clocks. And they published a paper, and Andrei has started a very nice collaboration called GPS.dm. It's using the GPS network as a network of clocks, and they are actually producing a lot of very interesting results. Now, actually, there is a very close collaboration between this GNOME, which stands for Global Network of Optical Magnetometers for Exotic Physics Searches. And so as this was developing, at some point, you guys published a very nice paper with one network of one clock. Yes?
Yes. And later on, we published a paper with a network of 5 clocks.
Yeah.
Everybody now has a network.
Yeah, network. But I actually always said that the networks of all sensors unite, or I guess no longer this no longer rings a bell with this audience, this kind of a joke. Okay, good. Now let me tell you about something that you don't know, because I don't know myself yet, but it turns out that in the late 60s, people have invented an amazing device, which is called a superconducting gravimeter. This is a superconducting ball that is sort of held in space, and you measure the feedback to the coils that hold it. and you can measure gravity to something like 10 to minus 11 to 10 to minus 12 g per square root of hertz. No clock comes a million times to this. You know this.
I know, because
This-
clock doesn't measure gravity.
Yeah, actually, you cannot measure potential either. So you measure difference in potential, and then, anyway, we can discuss. But this is a beautiful, beautiful device, and what do we know? There is a network of this, and not for dark matter, but because people are really interested in you know, how the core rotates, how the seismic activity happens, and it gets better. It gets better. The data from this network is publicly available. You go to your PC and you load it on your computer, and then you can do things.
But the problem is that this data are really big, because, for example, you think about Poland and Japan, every day the Earth breathes by 1 meter. So there's gravimeters really huge effects.
Yeah, so they have 3 levels of data. And there's raw data, and then tidal effects removed, and then other things removed. So you can, it's an interesting, we are really working on this at the moment. I learned about this from this guy, Alan Mills, who is actually not a dark matter guy. He's very famous as a positronium physics guy. He makes positronium sources. But he once had an idea. We were chatting about what each one of us is doing, and he had an idea many years ago about this, and couldn't make it happen, so now we're making it happen together. So what's the idea? Do you remember your high school physics? And there was this problem that if you drill a tunnel through the earth and you drop something, then this thing will come back. And the period is 80 minutes. And actually, this is the same period as, you know, the astronauts go around 90 minutes, and that's the same, actually, it's the same problem if you think about it for a few minutes. And when you solve this problem, you usually assume that the Earth has uniform density. All right, so before we get into the density, so the idea of this is that suppose that somehow some kind of matter that weakly interacts with normal matter is trapped inside the Earth. We call it hypothetical internally orbiting matter, HIO. Okay? What I think is a little elephant that's not interacting with the Earth is like, you know, swinging on an internal orbit.
There is no reason why it should be like that. Why not
Could be like this. Could be like this. Yes. Yeah. And then if you first think, as any normal uneducated person would think like I was, I think, oh, let's assume that the Earth has uniform density, and then you discover something really amazing. That this 80-minute period, okay, does not depend on whether it's going like this or it's going like this. It is because it's inside the Earth. It's a 3-dimensional harmonic oscillator, and the period is the same. Like many educated people knew it all along. And then the idea is, why don't we look for these 80 minutes in the gravimeters and see if there is this potentially dark matter element somehow flying around inside the Earth? Well, the first collision with reality happens when you type the structure of the Earth in the Wikipedia and you look up the density of the Earth. And what you see is this. This is mind-blowing. So at the surface of the Earth, if it's ocean, it's a density 1. If it's solid, it's about 3.5 or something. And then you go down, go down, go down. Well, it's okay. This is more or less uniform, but it climbs up to 4.5, from 3.5 to 4.5. But then there is this mantle core, liquid core boundary, and then the density jumps by a factor of 2. And then you go, and then there is a solid core, liquid core boundary, and it jumps further. And so you end up with a density of 13 point something, from 3 to 13. It's so non-uniform, ladies and gentlemen, that if you measure G, if you do drill a tunnel, and you measure G, you expect G to uniformly drop. It's not uniform. It's constant, then it increases, and then it drops. It's crazy. It's absolutely nuts. But nevertheless, you can, of course, rescue the idea if you assume, for example, that this dark matter elephant is not going very far from the center. Then it's actually, because the density is higher, it's a 55-minute period, and you can still look for it. But you can do some modeling, and it's much less beautiful than it would have been with uniform Earth, but nevertheless. Okay. So this is a picture of this gravimeter. This little ball, about the EA big. And this is the network, similar to the pictures that you had and I had. Anyways, we're having some fun with this. All right. Now, I need to tell you a couple more things, but just by naming them. I'm super excited about this, and this is about to appear in press. And this is the world's first dark matter search using antimatter. Dark matter search using antimatter. So it's worked together with the BASE collaboration. So it's at CERN. These guys trap individual antiprotons and keep them for months in bottles, and they measure. The main goal of the experiment is measuring magnetic moment of antiproton and comparing it to magnetic moment of a proton. Again, they had tons of data on disk, and these data were analyzed mainly by the work of Christian Smora, and Evgeny Stadnik was postdoc with me, and now he's at IPMU in Tokyo. No, if you believe in CPT invariance. But if all antimatter experiments are meaningless, if you assume CPT invariance, then you know the precision is not as high as with matter. But however, there are good reasons, I think, to try to expand this a little bit, because another elephant in the room, in addition to dark matter, okay, is why is that all the matter we see in the universe essentially is matter, and there is no antimatter? If they are so symmetric, where's the antimatter? But now imagine that dark matter interacts asymmetrically with antimatter and matter, and then you might actually answer a lot of interesting questions. So I think I'm super excited about this. And again, there are other groups working with antimatter. For instance, the alpha collaboration can probably do similar analysis, and I think it's a start of a very good new direction. Okay, so there are quite a few things that are going on. Some of them I already mentioned. Dark matter search with antimatter. That dark matter is like chaotic light. Then there is this Russell experiment for looking for fast oscillation, fast effective oscillation of constants. There is a discussion of possible enhancement of dark matter by the gravitational field of Earth and the Sun. That's the work with Gilad Perez and his team. Something I didn't talk about with my Chinese collaborators in Hefei, we have a maser. It's a optically pumped xenon spin maser with which we are also looking for dark matter, similar to the Casper experiment, and this is looking really good. We also are debating now with theorists who have been teaching us for a long time that the effect of these scalar fields is like variation of fundamental constants. And in fact, there are many subtleties here, and I think it's not always the correct description. So this is some theoretical work we are doing at the moment. And there is another interesting direction. When people look for these exotic dark matter particles, you don't really need necessarily to look for, say, galactic particles or make them or something. Their existence should also modify the known interactions to some degree and lead to effects like fifth force or something. And a lot of people are doing experiments like this, including us with antimatter. And there is a sort of a catalog of possible potential for different interactions, which was also published this year. So I think Michał already referred to this paper. It's a big review that was spearheaded by Mariana Safronova. It was published in 2018. It's actually about all kinds of fundamental physics that you can do with atoms and molecules, and I'm very happy to say that this is hopelessly outdated already 1 year after it was written. There's Mariana. She's such a wonderful colleague. She's so energetic and gets things done. Wonderful. So anyway, I think it's 3 o'clock and I should have some shame and stop here and not, unfortunately, with I'm very sad about this. I'm not going to tell you about this gamma factory unless you ask me a question. So I'm going to stop here provisionally.